Thanks for staying here, and as said, in return you get 2 speakers. And this is all about the VCSEL and the new standard, an IEEE standard that is being developed now for automotive, but then for automotive data interconnect. So I'm not talking about 3D sensing, but automotive interconnect. So we'll talk you through what the new standard is and the rationale behind this standard, why especially then the VCSELs of 980 have been chosen. And thanks for the previous speaker for introducing that topic already, and that this is no-brainer, and we want to convince you that this is indeed a no-brainer. So what we shall tell is the rationale why having optical interconnects in datacom after all, and this is all connected to the exploding data rates that you will see in automotive, especially high-resolution cameras, high dynamic range cameras that are going all the way up to 10 gigabit interconnects that are necessary to connect this to the central processing unit. And of course, this leads to the requirement of having optical interconnects. As you know, short-reach optical interconnects are well known in the datacom area, so in the data centers. And automotive, by definition, is short-reach. So the standard is talking about something below 40 meters, which is short-reach for these standards. And VCSEL-based multi-mode interconnects are proven technology there. However, there are distinct differences between data centers and automotive. As you know, automotive is requiring operating temperatures that go from minus 40 degrees all the way up to 125 degrees, which is a real challenge for optical components, especially lasers. And as the current designs are built on built-in interconnects and not pluggable interconnects, then of course the requirement on lifetime reliability is also an order of magnitude higher. 980 nanometer VCSELs, they have demonstrated in the past to fulfill these requirements. Of course, there's a lot more work to be done, but we'll show you some of the data of 980. It's not really our invention, and we're not the first to discover 980 is much more robust than 850. 850 is there because it has been chosen once, and then for interoperability, it has stayed there for the last 20 years in data center. But automotive is greenfield, so we can start all over again and make the best choice. There is a new standard, IEEE AO2.3CZ, which is addressing the automotive interconnect, and this standard is now fixed, close to being released, that standard, but it's almost fixed to 980 nanometer VCSELs, and that was, of course, a discussion that is based on the reliability data that have been presented. Now, KDPOF and TRUMPF, we team up to implement this, and KDPOF is the one who is telling about the full interconnect, and we are the humble suppliers of VCSELs and photodiodes for that purpose. Rubén.
Okay, thank you, Joseph. So the first question to answer is why optical interconnects in cars? And I have to say that the physical laws support the use of optical connectivity. And the reason is that the copper cables are reaching their limits at reasonable cost. Here in the right side, you can see the insertion loss of 11 meters of copper. This is the specification that we can see in another project in IEEE, also for multi-gigabit transmission. And you can see that insertion loss for about 7 gigahertz is about 30 dBs. So if you try to use longer cables, you will experience higher insertion losses. And if you try to run higher speeds, the problem increases. But insertion loss and return loss is something about signal integrity. There are other topics that are important. Is that the electromagnetic compatibility. When you have to operate in these very high frequencies, the emission of the noise and the immunity against the noise is much more problematic to solve. So link length and the amount of the connectors that can be used in electrical links is reduced. And on top of that, the aging produced by temperature cycling, high temperatures or the bending of the cable, etc., can produce some nulls in the frequency response that affect a lot the the performance of the system. So finally, the vendors of these cables need to design, to provide to the market rigid, heavy, and bulky cables, and providers of silicons, the PHY ICs needs to integrate costly DSP to compensate this insertion loss, the echo, and the return loss, etc. So, however, for optical, However, for optical communications, the response of the channel is completely different. You can see in green the response for OM3 fibers, OM3 fiber, 40 meters length. So we can see that there is no limitations in the reach. So we can address interconnecting sensors and brains in cars, trucks, and buses. So we are not limiting just to cars. And the number of inline connections that we can implement is much higher than in electrical connections. And optical fiber is superior in EMC, but it's very key in electrical cars. This galvanic, this is a dielectric medium, so galvanic isolation is produced when you connect two different ECUs that are in different voltage domains. For example, you may have an ECU that is in the high voltage domain of the battery and another ECU that is communicating with the previous one in the low voltage domain, but you don't have any problem, and you prevent also the ground loops that are very problematic for the noise emissions. So EMI and EMS is not a problem for this medium, and only for the electronics that is solved in the same way that the ECU at the ECU level. So optical fiber have a lot of advantages with respect to electrical connectivity for automotive applications.
So I take over back again to speak about the VCSEL properties, just 2 slides, and then Rubén will talk more about the system level. We have, in TRUMPF, we have investigated 980 to all the way up to 1065 nanometer VCSELs for many, many years. And especially one program we've run over many years with CWDM operation, where 980 was one of the wavelengths and 1065 was the upper wavelength. And there we have seen that if you design it properly, we can get, first of all, excellent electrical performance, which you can also get with 850, by the way. And here's an example where all the wavelengths, there are 5 different wavelengths, are operating between, so with a bandwidth of all the way up to 18 gigahertz, 3 dB bandwidth, which is well suited for 56G operation in a PAM4 mode or 28 gigabit per second in NRZ mode. We have tested them for HF performance. They show bandwidth, as I said. They have good damping and ISO. So basically, the performance is as required for what is needed in automotive, which will not be 56G in the first place, but eventually the standard should be should also enable the 56G, which would be met by that performance. We have in one of the following slides, we have also data that show the actual real time performance in a PAM4 mode at very low and very high temperature, so the -40 and the 125 degrees, as you will see in a minute. So what's the rationale and the benefit of long wavelengths? Now, for VCSEL experts, this is no news actually, but I would like to share some data. When it's about long wavelengths, and I would call long wavelengths above 940 nanometers, which is distinctly different from 850, then they can operate in general at much higher temperature, while maintaining the excellent reliability. So what we have done, and you see on the right side a number of stress tests that we have run with one of the 980 devices, where we run at a temperature of 170 degrees, which is an extremely high case temperature, and 6 milliamp, or on the bottom 140 degrees and 10 milliamps, both very severe stress conditions. Well, the whole population of that test after even 4,000 hours didn't show any significant change. Now, if you compare this with a standard 850, of course, some people may have improved on this, but this was industry standard at the time for an 850 device, then you can see on the dotted line that at the dotted line under the same stress conditions, you would see a 50% failure rate already after a few hundred hours or 1,000 hours. So therefore, the case for reliability and high temperature operation is very clearly in favor of the longer wavelength. That benefit is also the basis for having chosen that in the automotive standard, so it's 980. But the same is, by the way, also true for if you operate them at very high current density, which is necessary for 100G operation and even 100G in the new standard for datacom applications is widening up from 850 all the way up to 940. So the benefit is really wear out and random failure, and this is again confirming what is already known for experts for quite some time already. Now the test under the very low and very high temperature has been confirmed and carried out by KDPOF, and Rubén will explain this.
Thank you, Joseph. So in this slide, we show the performance of 980 nanometers VCSELs at a very low temperature, that is backside temperature of -40 Celsius degree and backside temperature of 125 Celsius degree. In this experiment, we have a bias current of 7 milliamps. We are modulating with an extinction ratio of 4 dBs. And we observe the signal after 40 meters of OM3 multimode fiber. We are running 53.76 gigabits per second using PAM4 modulation. So the equivalent baud rate is 26.88 gigabaud. So what we can see in the left side, in the blue eye diagram, is the signal that is received in the output of the fiber. So we have connected the output of 40 meters of OM3 to the digital communication analyzer, DCA, and we can observe the eye diagram for the PAM4. You can more or less distinguish the 4 levels, but you can observe some intersymbol interference that is produced by the low temperature in the VCSEL, but also because the effective modal bandwidth limitation in this wavelength that is very small, but can affect a bit the reception of the symbols in the receiver. In the right side, in orange, you can see another eye diagram. This eye diagram is the result of processing the blue eye diagram with a DFE equalizer. The DFE equalizer has been specified in the IEEE 803CZ standard to be the reference receiver that is used to qualify a transmitter that is going to be interoperable with this standard, and also to make the calibration of the stress receiver sensitivity. Okay? So you can see how the intersymbol interference is corrected by this DFE equalizer, and you can distinguish very well the 4 levels of the PAM modulation. The situation with 125 degree is worse, okay? Because the threshold current increase, the bandwidth decrease, and so in general the performance of the VCSEL is affected by high temperature. However, this is not a problem to establish a link with 50 gigabits per second, because the same kind of equalizer is able to compensate the distortion caused by the high temperature operation in this VCSEL. So you can see how the 4 levels of the PAM4 modulation can be distinguished using the DO3ZZ reference receiver. Okay? So it's important to understand that VCSEL is the light emitter, and it's very important that the performance is good in very extreme temperatures, and also the reliability as commented by Joseph. But we have also introduced in this Ethernet interconnect standard different techniques to be able to compensate distortions produced in photonics when these photonics operate in very extreme temperatures that are demanded by the automotive market. Okay, so let's talk about the DO3 CZ standard. This is the multi-gigabit optical automotive Ethernet task force. The code name is Omega. The call for interest was in July 2019. The task force was formed in June 2020, and we were developing all the specification, and the draft was technically complete to be moved to the working group ballot at March 2022. Today we are in the standard association ballot, and we expect that the standard will be released January next year. In this standard, we have a set of different Ethernet PHYs specifications targeted for automotive applications. So we have different PHYs to support different data rates. So in this standard, we support data rates between 2.5 and 50 gigabits per second, single lane, also supporting 5, 10, and 25. The only one that uses PAM4 modulation is the 50 gigabits per second rate. The 2.5, 5, 10, and 25 use NRC modulation. This standard supports implementations qualified according to ACQ 100 grade 2. That is the norm that the vendors, the 5 vendors for automotive use to qualify the integrated circuits. And grade 2 indicates that the system, the chip, the component has to support operation between -40 and 125 backside temperature. That is equivalent to 105 30-degree ambient temperature inside the electronic unit. This standard supports a maximum reach of 40 meters, so we are able to address use cases in cars, buses, and trucks for connection of electronic brains, for connection of radars, for connection of camera sensors, etc. And support low-cost, small-size, automotive-grade optical connectors, up to 4 inline connections, and also automotive-grade cables. This is a very important difference with respect to other standards in IEEE 803, because all the multi-mode communication links have been designed before to maximize the link distance. Okay? This standard is not optimized to maximize the link distance, but to maximize the supported channel insertion loss. We have a short channel that is only 40 meters, so we don't have problems with chromatic dispersion, we don't have problems with modal partition noise, etc. But we have to support very low cost in light connection that are going to have larger insertion loss. So if we want to have the connectors that can be used in the assembly plant of the cars, if we want to have connectors that are produced in very low cost, high volume, we have to permit high insertion loss, and this is what is provided by this standard. This standard also supports adaptive data-aided equalization and timing recovery for the best receiver sensitivity implementation, and to address a high production yield with high variations in the production process. This is very new for optical communications, because these PHYs can establish the link without I. Then, using these algorithms, open the eye and receive the symbols without inter-symbol interference. Also support advanced diagnosis, wake-up and sleep functions, and dependability functions that are very specific of the automotive applications, implementing a parallel operation administration maintenance channel, and support energy efficient Ethernet for big power saving in the receiver side. That is very useful for low traffic conditions or for asymmetric use cases. And support standard pick and place and reflow process with low cost co-package optics. And of course, as commented before, we are leveraging several components that are mature in other industries, data center industries like OM3, VCSELs, and photodiodes. Okay, so what will be the timeline for the market introduction? It's important to note that not only Ethernet can be the application of this kind of fiber optics interconnect in the automotive. We have also other use cases and other data interfaces that are used today in automotive industry, like CSI2 and PCI Express, that can benefit of the fiber optics. CSI2 is an interface specified by MIPI Alliance and is used by many sensors like cameras, radar transceivers, etc. PCI Express is an interface used for connecting CPUs and peripherals, memory to processors, etc. And there are other use cases that is very important. How to aggregate information coming from several sensors into a single fiber, and how to make this deaggregation in other points of the network. So the timeline needs to consider all the use cases that we want to support. So next year, then the first half of 2023, we will have the first engineering samples supporting the implementation of the 802.3 standard up to 10 gigabits per second. This will be only Ethernet communication. In the first half of 2024, we will have engineering samples also including capability to interconnect CSI2 sensors, okay, with data rate up to 12.5 gigabits per second. And in 2025, we will have production samples supporting Ethernet connectivity, CSI2 connectivity, and PCI Express connectivity. These production samples will be in that date under qualification according to AEC-Q 100. And finally, in 2026, we will have the next generation up to 25 gigabits per second, supporting also CSI2 connectivity and PCI Express connectivity. So we'll be able to double, more or less, the rate with respect to the previous generation. And that's all from our side. Thank you very much for your attention.
Perfect. Very interesting. So are there any questions? Okay.
Yeah, thank you, Thorsten Wibierski. I was wondering, one of the key requirements in automotive applications is the bending radius of the fiber should be very small. So that's a big advantage for plastic fiber or PCS fiber. And now you're proposing a high-speed OM3 fiber. Can you comment on the bending radius?
Yes, of course.
Thank you.
Okay, in the automotive industry, we have been using a step index POF that is 1 millimeter core, and I know some trials of using 230 microns PCS fiber, but without success. Okay, the bending radius that is supported by OM3 fiber 50 microns is smaller than a step index POF. The important thing is how the cable is implemented. You need to include around the fiber the right coating and the right strength elements in the cable to avoid that the fiber itself, 125 microns itself, experience the bending. But you can get with OM3 fiber with the right cable, we can use 2 millimeters radius or 2.5 millimeters radius without any problem. It's something that is not a problem. Yeah. It's really reliable. And in other applications like avionics or industrial automation, this kind of fiber is already used with no problems.
Anything else? Okay, sure.
Well, if nobody else has a question, I ask another question. You mentioned 980 nanometer VCSELs are, of course, better for high temperature. Totally agree. One of the reasons, or actually the main reason at the time that people chose the 850s was they want to use very low-cost gallium arsenide photodetectors. And for 980s now, we need like indium phosphide, indium gallium arsenide based photodetectors, at least for that kind of speed level. Can you comment on that? Is that the standard that you intend to use?
There are different options, but the well-established technology is indeed InGaAs technology, and this is cost-wise higher than gallium arsenide, but certainly within the budget of what is targeted for automotive. So we don't see this as a blocking item. So.
How about CG, silicon germanium?
I don't know. I don't know.
Hello. You've shown some pretty convincing data about lifetime of 980 nanometer VCSEL versus 850. Can you comment on the data, if they were the same class of devices, if they are like a market average? Can you just spend a few words on that?
I'm not sure if I got it. You're asking whether these devices that I've shown are the ones that would be introduced into. Yeah. Sorry.
Yeah. So if you have a comment on the 850 nanometer data that you see, if they are like exactly the same devices, or if they are represented to be an average of the performance, or if it's a particular.
So they're obviously not identical. So it's they are different, but in terms of power density, in terms of current density in the aperture, it's very comparable.
So which of the car manufacturers are supporting this new standard? Is it similar to the MOS standard or different folks?
Okay. In IEEE 803 Omega project, we have people participating in this standard that is affiliated with different OEMs. So people attending to the meetings from GM, from BMW, from Ford, different OEMs.
Great, thank you.
Okay, perfect. Then thank you very much again. Yeah, very interesting presentation.
Thank you.
And this, yes.